Nick is the recipient of this year's Office of Naval Research Young Investigator Award. Congratulations, Nick. And the title of Nick's talk is High-Speed and Reacting Flows for Applications in Defense and Sustainability. Nick, you're on.
Hi, folks. Maybe a little bit of a change for what I'm going to talk about today. I'm an assistant. My name's Nick Parziale. I'm an assistant professor in the mechanical engineering department. And I'll talk about 3 different projects that my group is working on. Novel means to make bio-oil, some strategies to help the United States Army deal with their munitions waste stream, and then some of my efforts with Air Force and Navy towards high-speed vehicle efficiency. So quickly to go through the novel scheme for bio-oil production, there's been a strategy for quite some time about how can we take the carbon that's in plants or stuff that doesn't compete with the food supply, how could we turn that into a useful oil, much like dead dinosaurs were able to turn into the petroleum that we end up using today. And so my research group came up with this strategy of taking corn stover, which doesn't compete with the food supply, take it and you put it in a high compression engine diesel motor, and much in the same way time and pressure turned hydrocarbon, turned a dinosaur into oil. We're able to turn biomass into oil in an engine with heat, maybe not time, but very, very quickly, something called fast pyrolysis. You take some biomass and you can turn it into oil. And we have a little image here of our oil being produced that I'd like to acknowledge the support of PSEG, which is a great thing that SES has let me be a part of. And so this is sort of the big sky motivation of what could you do with this sort of thing? So let's say we had one of these reactors, you can turn corn stover into oil. Well, what can you do? You can take it from the farm, put it to one of these processing plants and displace oil is the long and short of it. And maybe pie in the sky thinking, you could do maybe about a quarter of the US annual oil consumption. So there would be some impact there. Here's a picture of our setup, maybe a little too complicated. Here's a picture, again, some snapshots at the outlet on the left. What does this mist actually look like? And then I'll show you a picture of the reactor running. It's a single cylinder, for now, diesel motor, played a couple times, of this oil mist coming out. All right, moving on. So this project, parts of it are ITAR, so please forgive me for the bland slides and not much in the way of pictures. There's this stuff that Holston Army Munitions Plant makes. It's called ANSOL. It's ammonium nitrate solution that's 2/3 ammonium nitrate, amine nitrates, water, and a little bit of explosive. So basically, ammonium nitrate and amine nitrates in some water, and they make a lot of this stuff. And they don't really know what to do with it, and treating it is actually quite expensive. So our group in Christos's research center, Professor Christos in the Center for Environmental Systems, we're able to, he brought me on to think about this problem. And what we're thinking about doing is using the amine nitrates along with the ammonium nitrate to more or less make harmless stuff. You take this nasty stuff and you can react it in a high pressure reactor, a continuous flow reactor, and make stuff. Yeah, CO2 is not so bad, but it's not really not that great, but it's not nearly as bad as amine nitrates or ammonium nitrate that's tainted with other chemicals. And so we have something called differential scanning calorimeter, which just basically measures heat release. So you take some of this ANSOL, you put it in this device, and it gives us these nice curves on the bottom right, which tell us that the reactions that we think are taking place are taking place. And then finally, a lot of the research in my group is in aerodynamics, high-speed aerodynamics, and vehicle efficiency. So supersonic and hypersonic, things that are several times the speed of sound. Hypersonic being maybe 5 times or higher. You know, you could fly from Tokyo to LA in an hour. That sort of thinking. And actually, this week, Elon Musk, who's, you know, he's a pie in the sky thinker, but he actually got there, was tweeting out that he was going to have hypersonic spaceports around the world, and that would be something that, you know, he'd be thinking about in the future. Where that'll go, who, you know, maybe only he knows. What does my group do? Well, we think about ways to make measurements in these gas flows. So things that move at 5 and 10 times the speed of sound, you know, they're terribly difficult to make measurements in. And so what my group does is we try and think about ways in this little animation here. This is from any mechanical engineering or civil engineer, or almost any engineer who took fluid mechanics would have seen this video. We want to know the difference between what we call laminar or ordered flow and turbulent or chaotic flow. And that's true of wind outside. That's true of water in a river for Professor Hodges' work. That's true of flow over an F-22. Everybody's interested in the difference between laminar and turbulence because of higher rates of heat transfer, because there's more drag when you have these chaotic flows. So recently my group has said, well, you know, back in the day, we had this is a very low speed water flow, so a few miles an hour. They would be able to analyze these turbulent boundary layers by using very, very simple diagnostics. So my group and I, what we do is we say, well, things aren't the same as they were in the 60s in terms of electronics, in terms of cameras. We got really cool cameras. We got really cool lasers now. So maybe if we purchase some of these components and think long and hard about, you know, what is and isn't possible, we'd be able to make images like on the bottom left, like we do on the bottom right. So the bottom right is Mach 3 flow. So, you know, a few thousand miles an hour, not a few miles an hour. And why do we do this? We're interested in 2 things. One, we call it test and evaluation. So folks who are interested, of course, in the government, you can imagine there's defense applications, conventional prop global strike or rapid space access. They want to be able to measure, you know, the flow over one of their wings and know that it's right. And then the other bit is fundamental science. So we know very little about these flows at high Mach number just because there haven't been measurements there. And so, you know, we make a contribution there. And sort of the cap off achievement of my group probably over the last couple of years was we went to AEDC Tunnel 9, which is one of Air Force's wind tunnels. It is the largest high Mach number wind tunnel in the country. This is a Mach 14 wind tunnel here. For scale, that's a guy. I know that guy. He's about 5'10", to give you a sense of scale. Prior to our work, if you had asked how fast this wind tunnel was, if you brought your niece or nephew there, they wouldn't be able to tell you. They'd be able to tell you the Mach number, but not the speed. And because of our advancements, we were able to say, okay, well, you know, it's about 2 kilometers per second, 1.5, 2 kilometers per second. You know, and we were able to give that data to them, and they were able to go off and use that for important bits. So sort of a mishmash of several different research interests, but underlying all 3 things is an interest in thermochemistry, an interest in fluid mechanics. So thank you for the time.
Okay, thanks, Nick. Very exciting work, and I certainly hope Elon Musk is paying attention to what you do, right? I know you're well funded by the US Navy, but let's hope maybe Elon Musk will someday invest in what you do.
Yeah, sure.
Here as